Welcome to this explainer. Okay, picture this, raw, beautiful cotton fibers catching the golden hour sunlight. It looks so serene, right? But the journey from that delicate little plant to the clothes you're wearing right now, it is an absolute, meticulously engineered saga. Today, we're diving straight into how raw textile fibers undergo a total transformation into high-performance engineering marvels. It's an incredible story that fuses massive mechanical precision with advanced material sciences. Let's get into it.
Here's our roadmap for the day. First, we'll look at the context of textile mechanization. Then, we move to ginning, going from the seed to baled lint. After that, we'll navigate what I like to call the spinning metro map. Fourth, we'll check out high-speed yarn production. And finally, we'll wrap up with modern weaving and some wild future horizons.
All right, part 1, the context of textile mechanization.
So our journey actually begins way back with the old cottage industry model. Imagine a dim 18th century room where industrial textile production relied entirely on biological human labor, muscle and bone. Early weavers were completely trapped by rigid physiological barriers. Think about it. A weaver could literally only pass a hand shuttle as far as their own physical arm could stretch. That was the hard cap on production. That is, until integrated factory systems came along and totally replaced human muscle with relentless mechanical engineering, completely dismantling those old physical boundaries through high-speed automation.
Let's look at how fast things escalated on this timeline. In 1733, a guy named John Kay completely shattered human limits with his flying shuttle. This hammer-driven mechanism practically doubled weaving speeds overnight. But that rapid acceleration immediately caused a massive yarn deficit across Europe. So James Hargreaves answered the call in 1764 with his multi-spindle spinning jenny. Soon after, Richard Arkwright traded biological muscle for serious hydrodynamic power using continuous mechanical drafting rollers in his water frame. And finally, by 1822, Richard Roberts brought the whole mechanization era to full maturity with a massive cast iron power loom that used precise metal engineering to perfectly control fabric tension.
Now take a look at this number. What's absolutely wild here is the sheer scale Samuel Crompton achieved back in 1779 with his spinning mule. This machine was the structural zenith of the era, essentially a hybrid combining all that previous tech. A single machine could effortlessly command up to 1,320 spindles at once. It manufactured incredibly fine, ultra-uniform yarn at an industrial scale that people back then could barely even comprehend.
Okay, moving right along to Section 2, ginning. From seed to baled lint.
Jumping from historical automation into modern raw materials, we immediately hit our first massive mechanical hurdle. How do you separate the valuable cotton from its biological matrix? Well, when seed cotton is vacuumed up into a gin, it has to be dried out to a very strict 5% moisture level. If it's too wet, it completely clogs the machine. Too dry, the fibers literally snap. But when you get that perfect balance, the output breaks down roughly into 55% seeds, 35% lint, and about 10% trash.
Here you can literally see the visual contrast. On one side, we have that pure, fluffy 35% lint. That's the gold. That's what we desperately need for textiles. And on the other side, that 55% fuzzy seed byproduct. Now don't worry, those seeds definitely don't go to waste. They're actually highly valuable and get redirected into making things like oils, plastics, livestock feed, and even cosmetics. Now, to efficiently transport all this extracted lint to spinning mills across the globe, we use massive hydraulic machines to squash the fibers under immense pressure. They're packed into these incredibly dense, brick-like bales that weigh exactly 227 kilograms each. Just to put that into perspective for you, that is roughly the weight of an adult grizzly bear.
Next up, Section 3, the spinning metro map.
Okay, so once those iron-hard, grizzly bear-sized bales actually reach the factory floor, they enter this crazy labyrinth of divergent processing routes. It seriously looks like a complex metropolitan transit map. But no matter what kind of yarn you're trying to make, every single route has to pass through 3 mandatory stops: the violent winds of the blowroom, the meticulous untangling of carding, and the parallel leveling of drawing. It's exactly like prepping all your ingredients in a kitchen before you can actually start cooking a dish.
So, Step 1, the blow room. I want you to imagine this as a highly violent environment. Those 227 kilogram bales are battered and whipped around by high-speed air. This separates the fibers and blasts away any remaining leaf trash, effectively opening them back up into soft, usable cotton.
Step 2 is carding, which is widely considered the absolute heart of the spinning process. Think of it exactly like using a fine-tooth comb on a toddler's severely tangled hair. Millions of tiny needles comb through the fibers to untangle the chaotic web into a continuous, untangled rope called a sliver. If you don't execute this step perfectly, even the most insanely expensive modern spinning machines will constantly just snap the yarn in half.
All right, Section 4, high-speed yarn production. After those foundational prep steps, our little metaphorical metro map wildly diverges, and it all depends on what the factory values more: supreme, flawless quality, or blinding, unbelievable speed. On the left here, we have the slow, premium route called combed ring spinning. That's what creates the super smooth fabric for high-end dress shirts, and it ends by neatly wrapping the yarn onto a cone. On the right, though, we completely bypass several steps for the sheer, friction-driven velocity needed to mass-produce cheap t-shirts. Because of that extreme speed, the yarn is instead wound into this big cylindrical shape that the industry literally calls a cheese.
So why is that premium combed route on the left so much more expensive? Well, it's because the combing machine acts as a totally ruthless gatekeeper. It violently ejects 15 to 20% of the short, weaker fibers straight into the trash. And while that sounds like a massive loss of material, it's absolutely crucial. It guarantees your final garment won't pill or produce those annoying fuzzy bubbles on the surface over time. Now, this brilliantly illustrates the ultimate hybrid approach, air-jet spinning. In this method, no mechanical parts even touch the fibers to twist them. Instead, it uses untouchable hurricane-force compressed air. But there is a catch. To pay the tax for using this chaotic air vortex, the factory has to draw the fibers 3 separate times until they are flawlessly 100% parallel. Otherwise, those high-speed winds will just blast the fibers totally apart.
And finally, Section 5, Modern Weaving and Future Horizons.
So our perfectly spun yarns have finally reached the modern weaving shed. And let me tell you, this place is entirely unrecognizable from those hand-operated wooden looms of the 18th century. As you can see on this table, modern shuttleless technologies offer some incredible trade-offs. Check out the blistering 1200 RPM speeds of air-jet looms. They literally shoot yarn across the fabric using compressed air. Conversely, look at the unmatched 16-color versatility of mechanical rapier grippers. They operate a bit slower, but they can flawlessly handle everything from delicate fine silks all the way to heavy industrial fabrics. As we look back at how far we've come, escalating from the physical limits of a single human arm to highly automated robotics capable of inserting yarn over 1,000 times a minute, I want to leave you with this provocative thought. With AI and robotics advancing at an absolutely breakneck pace, will the machines of tomorrow eventually eliminate the factory entirely? Could we see a future where robots are out in the field, plucking and spinning the cotton directly from the soil? There's no way to know for sure just yet, but think about that the next time you pull on your favorite shirt. Thanks for joining me on this explainer, and as always, keep questioning the world around you.